Dear friends, today we will discuss a problem as the application of maximum modulus theorem. Okay, let fz be a function that is analytic on the bounded domain omega and continuous on omega bar. Suppose that fz is non-constant on omega. Prove that if mod fz constant on boundary of omega, then fz must have at least 10 in omega. Okay, actually this problem can be solved using maximum modulus theorem. So first we state the maximum modulus theorem. Okay, maximum modulus theorem. This problem is an application of maximum modulus theorem. Okay, let omega be a bounded domain in whole complex plane C, and f is continuous on closure of omega, that is actually omega union the boundary of omega. Okay, and f is analytic on omega. Okay, see, f is continuous on omega bar. Okay, and omega is bounded, so omega bar is compact set. So omega bar is compact set and f is continuous on omega bar. So supremum of mod fz exists on omega bar. Okay, the result is supremum of modulus of fz is same as supremum of mod fz where z belongs to boundary of omega. Okay, so this is the maximum modulus theorem. This theorem states that if f is analytic on a bounded domain omega and continuous on omega bar, then the supremum of modulus of fz on whole omega bar is same as supremum of mod fz on the boundary. Okay, so given omega is bounded domain, f is analytic on omega, and f is continuous on omega bar, and also it is given that f is non-constant on omega, but mod of f is constant on boundary of omega. Okay, the claim is fz has at least one zero in omega. Okay, so we have to prove this result by method of contradiction. Okay, so let us assume that fz has no zero inside omega. Okay, then obviously 1 by f is analytic on omega, and 1 by f is continuous on omega bar. Okay, since omega bar is compact, okay, why compact? Because it is closed and bounded in C, so it is compact, and modulus of fz as well as modulus of 1 by fz is continuous, so their supremum exists. Supremum of mod fz on omega bar exists, as well as supremum of 1 by mod fz as z belongs to omega bar exists. Okay, so by maximum modulus theorem, the supreme value of mod fz as z belongs to omega bar, this supreme value is same as supreme value of mod fz when z belongs to boundary of omega, and supreme value of 1 by mod fz is same as supreme value of 1 by mod fz where z belongs to boundary of omega, right? So from these two equality, we can conclude that the supreme value of mod fz where z belongs to omega bar and the infimum value of mod fz where z belongs to omega bar both lies on the boundary of omega. Okay, also it is given that mod of fz is constant on boundary. Okay, so we can conclude that the supreme value of mod fz is same as the infimum value of mod fz where z belongs to omega bar, right? That means modulus of fz is constant on omega bar, hence in omega. Okay, now omega is a domain and mod of fz is constant on omega. So obviously using CR equation we can show that the derivative of f dash z is 0 on omega, that is fz is constant on omega. Okay, but it is given that fz is non-constant on omega. Okay, that means our assumption that it has no 0 in omega, that is not possible. So fz has at least 1 0 in omega, and this completes the proof. Thank you.